Welcome to solverfy.
We're given a weighted graph, and we're asked to find a spanning tree with minimal total weight that contains two edges from this weighted graph. So the weighted graph is the one in figure 3 from the book in this section. And we're asked to find a spanning tree with the minimal total weight containing the edges EI and GK. So to do this, I'll use Kruskal's algorithm. So first of all, I'll construct a graph which consists only of the vertices of the weighted graph. So this is the vertices A, B, C, D, E, F, G, H, I, J, K, and L. And to start off, we'll first add the edges EI and GK as we're required to do. And these both have a weight of 4. And now we'll be applying Kruskal's algorithm to determine the remaining edges. So we have that the smallest weight of the remaining edges of 1 occurs between B and F, C and D, and K and L. So first, if we add BF, we see that we don't create a circuit, so this is valid. If we add CD, we don't create a circuit, so this is also valid. And if we add KL, we don't create a circuit, so this is valid too. Now, in the remaining graph, the smallest weight, which is 2, is between A and B, between C and G, and between F and J. So first, if we add A and B, we don't obtain a circuit. This is valid. If we add C and G, we don't obtain a circuit, so this is valid. If we add F and J, don't obtain a circuit, so this is also valid. And in the remaining graph, the smallest weight, which is 3, has many associated edges. So we'll want to choose edges that do not cause any circuits. And notice that because we still have, well, the number of vertices in this graph is 12, and we've only added 8 edges, we still require 11 minus 8, which is 3 edges. So I want to find 3 edges to add, make this a connected graph, to have the minimum weight of 3. So first of all, you could consider AE. So if you draw AE, you don't create a circuit, and now you connected A and E together. Consider BC. So if you draw an edge from B to C, now that there's 2 connected components that become 1 connected component, and we don't create a circuit. And finally, we still need to connect H to the graph. So consider GH. If we do this, we don't create a circuit. Now we have a connected graph. And so it follows that by Kruskal's algorithm, it follows that this graph is a minimum spanning tree with edges EI and GK. Included. And in summary, well, you can see from the graph what the edges are that are contained in the graph. I'd just like to point out that in that last step,